I wanted to sort of hyper briefly recall what has to be recalled from yesterday's lesson. So I introduced a bunch of models which belongs to this class of kinetically constrained models. What you have just to have in mind for the first part. So first of all, we'll make a break at half a lesson as by the organizers. So in the first half of the course, you can simply keep in mind one of the choices of the constraints that I introduced in yesterday's lessons, which is the is constraint, in which a site which says that prescribes that in order to be able to update a site, I have to look at the right of this site and check whether the right neighbor is empty. This is in one dimension. Let's say in one dimension for the moment, and for this is constraint. So what I meant to write here, sorry for the white slide, was that we had introduced our Markov dynamics and its generator, and you'll just have to recall for the remainder of this first part of the talk that the generator of the Markov process corresponding to the East model acts on the local function as it is written here. Namely, we update, we have the sum over all the site of a function C, which is giving us the constraint on that site, which is 1 if the site to the right is empty and 0 otherwise. And then the update puts the equilibrium measure on that site, where equilibrium is the equilibrium measure on that site with respect to the Bernoulli measure, which gives weight 1 minus q to occupied sites and q to empty sites. Okay, and the other thing that it's useful to recall that we introduced yesterday is this Dirichlet form, which is a positive form which corresponds to the mean over the equilibrium measure of the function times the generators applied to that function. And this form can be written as a sum, as a mean over a global mean over the whole space of a sum over all sides of these constraint functions times the local variable on that side. Yesterday, we saw that there is a critical density, critical value of this external parameter Q, which determines the equilibrium density of empty sites, below which convergence to equilibrium does not occur, and above which convergence to equilibrium occurs. Now we want to analyze more the regime in which convergence to equilibrium occurs and try to understand how this convergence occurs, if this occurs exponentially fast or slower than that, and at which speed. In order to do that, we have to introduce our main quantity for this for today, which is the spectral gap. The spectral gap is the spectral gap is the first non-zero eigenvalue of the generator. The generator is negative, so the spectral gap corresponds to the in the variational forms corresponds to the infimum over all functions which are not constant, because on a constant function the eigenvalue is 0. It is not modified by the generator of the ratio between the Dirichlet form, so minus mu of f generator times f divided by the variance. And a spectral gap, this variational formula immediately implies that if the spectral gap is 0, the variance of the function evolved at time t decays exponentially to the equilibrium variance with a speed which is governed by the spectral gap. Okay, we will sometimes also refer to the inverse spectral gap by calling it a relaxation time, since it's a time scale that gives this relaxation to equilibrium. Then is another way. So this inverse of the spectral gap is a first way to quantify a time scale for these models. Another time scale, which will be essentially equivalent in the regime which interests us, so in the regime of small density of vacancies, is the first time at which a given site, say the origin, since we have translation invariant, so can choose any given site, is first set to 0. So this, the heated time of this event that the origin is set to 0 can be studied via the can be up. Let's say we are interested in understanding how this heating time evolves under the stationary process, which is started from the equilibrium measure. And it turns out that this heating time is upper bounded again by the relaxation time, but with a correction which is dividing these infection times by the density of empty sites. Why? Because simply, as for any heating time, we can use the fact that the probability of that this heating time is so here is larger than t is exponentially suppressed with the speed here, this lambda, which is given by a variational formula, which is quite reminiscent of the variational formula with for the spectral gap, with the only difference that the function on which I have to minimize have to be 0 on the set I want to hit. So here on the set of configurations that have the origin 0. So this variational formula leads immediately to the fact that this speed of convergence to speed of decay to 0 of this probability is governed by the spectral gap is at least as fast as the spectral gaps times the mean of the set I want to hit. Here the set, the origin is 0, so mean under this initial measure from which I'm starting from. So in this case, the formula follows, so that the heating time under the stationary measure is again quantified by this relaxation time. So this provides only an upper bound for the infection time. In general, we don't have there's not a way to, it will be, say, model dependent. The way we will study the lower bound is infection time. But what we can say in general, which follows from the relationship with the underlying deterministic algorithm, the bootstrap algorithm, which is which we saw yesterday, and which is the algorithm in which in parallel and sequentially all the sites in which the constraint is satisfied are emptied. From this, under these dynamics, we can similarly define a heating time of the event that the origin is empty. So this heating time I'll call tau 0 BP. So it's the heating time under the bootstrap process, starting from the equilibrium measure. So I start from a configuration which is distributed with equilibrium measure, and I apply the bootstrap map, this map which is deterministic and that empties all the sites which have the constraint satisfied. Then there is a general, but sometimes very far from the real behavior, lower bound, which says that the mean heating time for the stochastic process, so the one for the KCM, this tau 0, is lower bounded modulo a constant by the one for the bootstrap. Why? So this is simply because so there is nothing complicated here. Simply have used the fact that essentially the bootstrap procedure, the bootstrap algorithm does not produce field sites, it only empty sites. So it is, if I start from the same configuration for the stochastic KCM dynamics and for the bootstrap dynamics, the bootstrap will, let's say, follow the most direct path, which is going to infect the origin. of course, there is here the difference between continuous time and discrete time dynamics of the bootstrap, but and the fact that the bootstrap is occurs in parallels, hence this delta here, which depends on the choice of the constraints, but it's very easy to establish this inequality. It's very natural. Okay, so now that that we know that in order to study this speed of relaxation to equilibrium, you have to look at the spectral gap. In the remaining time for the first half of the lecture, I'll try to give you at least one proof in not complete, but at least the main ideas for one proof. So how to prove that the relaxation time for the East model is finite, so that its spectral gap is larger than 0. Okay, so we are here in, as I said, in one dimension. So we have the model on Z, and recall that I can define the model also on a finite volume, provided I define a boundary condition on this finite volume. In particular, what enters in the dynamics for the boundary condition is only the value. If I have an interval and I want to know to study a finite interval, I want to study the dynamics on that finite interval. The only thing that matters is the value of the configuration just to the right of that interval, because the site to the right of that interval is the only one that enters in the constraint. And if I want the dynamics on finite volume to be ergodic, so to be able to relax to equilibrium, I have to choose an empty boundary condition on the right. Otherwise, the rightmost side of my interval will never be able to update. Okay, so our goal here will be to study the spectral gap in infinite volume, what I call gap, and to lower bound it by considering the infimum over increasing volumes, but finite volumes, of the spectral gap with the empty boundary conditions. Okay, so I can always use a standard procedure to go from the infinite volume to the finite volume, provided, and I have this lower bound, provided I can control uniformly on increasing volumes the value of the spectral gap. I can bound it away from 0. Okay, so our goal will be to prove that this value, that this quantity, which is called gamma k, which is the inverse of the spectral gap on the volume lambda, is upper bounded by the same quantity, but on a smaller scale, on scale k minus 1, times a prefactor, this ak. And we want to do this to establish this inequality in a way that we can iterate it and prove that we remain uniformly bounded, so that gamma k, the supremum over all gamma k, remains uniformly bounded away from infinity. Okay, so so here what I intended to write with my pen was that what you have to keep in mind is the variational definition of the spectral gap that we just gave. So the fact that saying that the inverse of the spectral gap is upper bounded by something is, so saying that gamma k is smaller than ak times gamma k minus 1 is the same thing as saying that the variance of any function is on the volume lambda k is upper bounded by the Dirichlet form on the same volume times this factor ak times the gamma at scale k minus 1. Okay, so establishing this iterative inequality means establishing inequalities between the variance and the Dirichlet form on scale k, with prefactors that depends on the spectral gap at k minus 1. Okay, so what is the idea here? So I want to connect the dynamics at scale k to a dynamics on a scale k-1, which means taking the volume and dividing it in two. Okay, so our volume lambda k is an interval 0 to k. I divide it in two, these two volumes B1 and B2 on scale k-1. So, and I consider a small region inside the volume on the right, which is of scale 2 to the k divided by 3. So much smaller than the scale 2 to the k when I will be considering scales that k that increases. So now that I have this, that I have divided my volume in these two blocks, I define, in order to go and study the upper bound, the variance on scale lambda k, I define an auxiliary block dynamics, which is this auxiliary block dynamics is a very easy dynamics that goes as follows. I have just two clocks, two exponential clock of mean time one clock on the block on the left and one clock on the block on the right. So one on B1 and the other on B2. When the clock on the block B2, the block on the right, rings, what I do is I throw away the configuration on the block B2, and instead of that configuration, I refresh the whole block B2 with a new configuration, which is sorted with the equilibrium distribution on the block B2. So with I update the configuration on block B2 according to the Bernoulli measure on that block. Instead, when the clock rings on the first block, so on B1, I do this update. So I update with respect to the product measure on that block, if and only if a certain constraint is satisfied. And the constraint is that if I look at the stripe I, which is contained on the second block, just on the right of the first block, there is at least 1 0 on that stripe. Okay, see, this is sort of a baby KCM. It's just a KCM on two sides, which are the two blocks, but with a configuration space which is more complex than having just 0, 1 variables. Is the configuration space is the whole configuration space on block B1 and B2.
Cristina, sorry, there is a question in the chat.
Okay.
So is it essential that I be on the left hand or B2 adjacent to B1? Can you read the chat? Otherwise, I repeat.
Okay, perhaps you can read the chat because I'm afraid of, I have the full screen. So the question is,
so if it is essential that the interval I is
yes,
on the left hand of B2,
yes,
adjacent to B1.
It's essential. We will see in a second why it's essential. This is, for the moment, is just an auxiliary dynamic. So I'm defining another model. And as we will see, it's essential that I is not contained in B1, and it's contained in B2 just on the right of B1. Okay. The first easy observation is that this auxiliary dynamics is reversible with the same invariant, with respect to the product measure on the whole volume, because I'm just if I start from the measure which is product on the whole volume, since each time that I make an update, I refresh one of the two blocks with respect to the Bernoulli measure, which is product, we will stay invariant. The other observation, and this is an easy calculation, but you have to believe me, because it's just a two-side, this is just a two-side configuration space. And it's very, so you simply have to write the 2 by 2 matrix, and you will discover that the inverse of the spectral gap for this dynamics is inversely proportional to 1 minus square root of the probability that the event which allows me to update block B1 is satisfied. The square root of the probability of the complementary, sorry, of that event. So, say if I had no constraint, if I was updating the two blocks at rate 1, trivially the relaxation time of this block dynamics would be 1, because each time the clock rings, I update. Since I'm adding this constraint, this relaxation time is larger than 0, and so it's and the larger is the probability that I do not satisfy this constraint. Okay, so I have for this auxiliary block dynamics a relaxation times that goes to 1 when k goes to infinity, because the probability to have at least one empty site with respect to equilibrium in that stripe, in this stripe I, is 1 minus q to the power cardinality, to the cardinality of this stripe. So since the stripe is of size 2 to the k divided by 3, this probability of not having at least one empty site goes to 0, but it's not 0. So it's the fact that this relaxation time is given by this quantity is the same as saying that if I write if I rephrase things in terms of the spectral gap for this block dynamics, the variance of any function on my volume is upper bounded by this relaxation time. So this the inverse of the spectral gap for this block dynamics times the Dirichlet form for this block dynamics. And the Dirichlet form for this block dynamics, if you remember what I showed before for the KCM, is not difficult to understand that it will be simply the sum of two variances, the variance of the block B2, just without any correction, and the variance of the block B1 multiplied by the function that is containing the indicator function that the constraint which allows me to update block B1 is satisfied. Okay, this indicator function of the event H that is telling me that there is at least 1 0 on that block. Okay, so I just rewrote the same formula because I knew I was changing slide. So this inequality, for the moment, I've not used the dynamics of the East model. I just wrote an inequality which follows from the study of these two-site block dynamics. Now, my goal will be to introduce the East dynamics here. So and in particular, my goal will be to be able to upper bound the right-hand side, now not with this Dirichlet form for the block dynamics, but with the Dirichlet form for the true dynamics, for the dynamics of the East. Recall that the very definition of the spectral gap it corresponds to the fact that the variance of any function over the given volume is upper bounded by the inverse of the spectral gaps times its Dirichlet function. So here one could be tempted to say, okay, but on the right hand side I have the sum of two variances. Why don't I upper bound each of the two variances with the corresponding relaxation time for the East dynamics times its Dirichlet form? Since the Dirichlet form of the East dynamics is simply a sum over all sides, I will obtain something which, if I upper bound each of these two terms, this one and this one, with the spectral gap, inverse of the spectral gap for the East dynamics on that volume, times the sum over all the sides of the volume with the constraint function times the local variance, I seem to have reconstructed the Dirichlet form of the original East model, but on the larger scale, with the correction factor here, epsilon k, which, as I said, converges to 1 and very fast when k goes to infinity. So we would be very happy because we have found that the variance here is upper bounded by the spectral gap on the smaller scale, inverse of the spectral gap on the smaller scale, because the dBi on the smaller scale, times the Dirichlet form. But the problem is that that's not working, because and that's why we introduce this. We have to introduce this this constraint here. This constraint that is requiring for the first block to be updated only if I have at least one empty site just on a certain stripe on the right. The point is that when I write this Dirichlet form for the volume on for the dynamics on the smaller volume, I'm using I have to take into account the boundary condition on those volumes. And while on volume B2, which was the volume on the right, I had outside the original system already had the empty boundary condition. Instead, on the first volume on B1, instead on the volume B1, so on the first half, I don't have in principle an empty site just on its right, this corresponds to the fact that if I want to evaluate the spectral gap or the relaxation time for the first volume with an arbitrary boundary condition, the one which is imposed by the fact that the block dynamics is performing the update on that volume, if the boundary condition on the right is arbitrary, it could have an occupied boundary site. And if the boundary site is occupied on finite volume, I know that I cannot relax to equilibrium because the last site of the volume on the right is never updatable. So it means that its relaxation time is infinite. So I cannot hope to use directly these inequalities on the smaller volume because of the fact that the boundary condition for the volume on the left is not the good one, is not with the empty site. So that's the reason, and you see why I really had to impose that stripe on my right. That's the reason why I was updating the block B1 only if there was at least one empty site on that stripe, because then the trick is to treat the variance on the first block by enlarging it to the random block which contains the block B1 and a little bit more. A little bit more is a part of the stripe I until just to the left of the first empty site that I meet. There will be one, thanks to the fact that I have this constraint, which is requiring an empty site there. And thanks to this fact, now I can, this is just some formulas, but I can, now I can really upper bound the variance on the first block by enlarging it using the convexity of the variance. One can enlarge this variance to the bigger random block C, which is going up to the first empty site. And now on that volume, I really have the good empty boundary condition to the right, the same that I had to the right. I have all the time to the right of block B2, thanks to the external boundary condition. So the moral of the story is that using these two block dynamics, we are able to upper bound the variance here on the whole scale k, so on the interval 2 to the power k, with what? With the spectral gap on the smaller scale. See that, okay, there are some adjustment to be made because B1 and B2 are on scale k-1, but B1, the random volume C is a little bit larger, okay, but it's just a matter of technicalities. But the point is that enforcing this constraint allows one to deal with dynamics on the smaller scale, which have the right boundary condition, so that they are really dynamics which have a positive, a spectral gap with the right boundary condition, so a positive one. Once we have this inequality for the variance on the whole volume, it's easy. So the only point is that we have counted twice. So there is a contribution which is twice for all the sites which belongs to this little stripe I, because they both appear in the dynamics to upper bound the variance on block B2 and to upper bound the variance on the block B1 enlarged up to the first empty sites. But then one can average on the position of this stripe, so change the definition of the dynamics of this block dynamics and moving around this stripe and conclude the proof that the inverse of the spectral gap on scale K is upper bounded by a constant AK times the inverse of the spectral gap on scale K minus 1, where this constant AK is such that if I multiply all the constants on all the scales and up to infinity, this product remains finite. Essentially, this AK is this relaxation time for the block dynamics on times K, so which scales as 1 over 1 minus square root of the bad events that I don't have an empty site on the stripe, with a minor correction due to the fact that I have to average on the position of this stripe. Okay, so iterating this inequality, one obtains the fact that gamma, so the supremum over all K of gamma K is finite, which corresponds to the fact that the spectral gap on the infinite volume is larger than 0. Then a natural question, I would say, after this all this speech about the East model is, since I gave you different choices of constraints, is to try to understand whether this proof that I made, I sketched, is very much dependent on the one-dimensional character of the constraint of the model that I'm looking at, and on the oriented character of the constraint. I'm looking at a very special constraint, which is the East one, which just goes and looks to the side to the right. So a first question could be, for example, for the other model that we introduced, one of the other models we introduced yesterday, the one in which we have we require at least 2 empty nearest neighbor. There is no orientation, this FA2F model, and we are in 2 dimensions. What happens? How can we modify this technique? Is it a robust tool to study, to determine that the spectral gap is positive, and so that we have exponential convergent to equilibrium? So let's try. If we are for the FA2F dynamics, and we try to do exactly the same, to follow the same route, what would be doing? So we take a volume, and first of all a finite volume, and we would like to determine an iterative inequality on the relaxation time on a certain scale, upper bounding it with the relaxation time on the half that scale. So first of all, we have to be very careful to choose boundary conditions which are such that the inequality I'm writing are meaningful, in the sense that I don't want to have boundary condition for which already the relaxation time is infinite. So I have to choose boundary condition which guarantee that in finite line I can connect any 2 configurations, otherwise the relaxation time is infinite. So one such configuration, boundary condition which guarantees ergodicity for this model is just to choose completely empty sites on the top and on the right boundary. Because you see, if on the top and on the right boundary we have empty and a frozen boundary empty configuration, then we can start, suppose even that we are in the worst configuration in which everything is occupied, then we can start on the right top angle here and that site is on the right top angle as this constraint which is satisfied thanks to the two empty neighbor on the boundary. And iteratively from that, we can start to empty sequentially all the lines. So this is a good boundary condition to start with. And in the same way, it's easy to see that for any finite volume, it is enough to have even not a square volume. It is enough to have a boundary condition which is empty in the north and right boundary. So one natural thing one could try to do is to consider when I consider the FA2F model to define a block dynamics in which when I cut into two blocks my scale K, in which the block on the right again has the constraint which is satisfied thanks to the boundary condition, so it can flip freely, so no constraint on that. But the block on the left needs some boundary condition in order for the finite volume dynamics to have a finite relaxation time. And for that, one possibility would be to require on the stripe in the middle to have a path, a top-bottom crossing of empty sites. That would be enough to guarantee ergodicity for the volume on the left, because once we have a volume which has a boundary, consider the whole volume, that I would like to color here with my pen, the whole volume of the, which is composed by the volume B1 plus everything on the left of that snake going down, which is a crossing of empty sites. All that volume has a boundary condition which guarantees that I can connect any two configuration in finite volume. So it has a finite, a positive spectral gap. And we could follow the same line as of this proof to prove positivity of the spectral gap for this model by using as a constraint imposing the occurrence of this crossing. If we do like that, we succeed in proving something, but something which is not very satisfying, because the probability of, so for the, in this case, for the block dynamics, the relaxation time will be upper bounded, but will be going to 1 when K, so the size of the volume, goes to infinity, only if we are Q, the value or the equilibrium volume Q is in a regime such that we have with high probability a crossing of empty sites. So only if the value, the density Q is bigger than the critical density for site percolation. So this is not at all the critical density at which blocked clusters percolate for this FA2F. As we saw yesterday, so this actually for this FA2F dynamics, at any value of the any positive value of Q, blocked clusters do not percolate. So the critical density of bootstrap percolation for FA2F is 0. So we have to be able to send to go down to extend this proof down to Q, which goes to 0. And in order to do that, one has to complement this, this sort of bisection constrained procedure that we used for the East. So this constraint procedure of doing a bisection and considering a constrained block dynamics. We should complement that with the other tools, which will be seeing later on. So some renormalization plus on some blocks. So not considering blocks being just single empty sites. Otherwise, we will be blocked to a critical to a density. We will block to a threshold density which has nothing to do with the critical density, which here is 0. Okay, so I think I'll stop a second because of making a break in half. And in the second half of the lesson, there won't be variances, complicated proofs, but just drawings. And hopefully I'm also connecting to something which has a pen which is working.
Okay, thanks.
5 minutes, how many? Yeah, yes.
Let us first, let me ask if there are questions.
Yes.
Yes.
Hi, I have a question about, do you analyze AKs for low values of K? And how do you see the K naught for which the tail ends up being a finite product?
And for the East model?
Just for these models, right? So you're saying that the necessary condition to get this contraction is that you need the product of AK from K naught to infinity to be finite. So if you say the AKs are defined according to this formula. So for low values of K, do you see that do you see a pattern in the AKs? Like, are they gradually, are they monotone in some way already?
Yes, we will be, okay, I switched to FA2F, but we'll be seeing in a second what is the, where we should stop. So it's, I think it's over 1 over Q, the value where we have, so when Q to the K is 1 over Q, where you should stop. And anyway, any value, I mean, on any finite volume, the point is that on any finite volume, the spectral gap is strictly positive. So the relaxation time is finite. So if I just want to establish that the relaxation time is finite in infinite volume, I can stop my iteration on any point. The point is that so I can start saying that I know that the spectral gap on size whatever you want is finite or any fixed size, and then in order to, what I have to do here, the task is to go to make a uniform bound when the size goes to infinity. So this task is to, so it's not a, so if the question is if it matters where I stop, it's not a, it's not at all a deal. So here I'm not studying for, I'm not yet discussing the behavior when Q goes to 0.
Is there some other, any other question? So, okay, thanks. So if not, let us have a break.
So, let's now go to go back to the East model and try to understand the scaling when Q goes to 0. So for the East model, by the way, it's clear that there won't be any blocked cluster whatsoever. So with probability 1, with respect to the initial measure, which is taken with the Bernoulli, I will be able to empty everything. Why? Because simply because if I'm on Z, I'm sitting somewhere. In order to be empty, I just simply have to have another empty site on my right, and starting from that, I can empty everything until reaching that site. So as long as I have an empty site somewhere to my right, I will be able to empty myself. Okay, so the critical density, so QC bootstrap percolation for the East model is 0. Okay, and we just proved that, in fact, that the spectral gap is larger than 0 up to that density. And now the interesting point is to study how does this spectral gap, so inverse the relaxation time scales when Q goes to 0. Okay, the answer, which I gave you already yesterday, so I gave you it in terms of the mean infection time, but we saw that the two quantities essentially up to Q square factors are the same. The answer is that this inverse of the spectral gap scales as exponential of log Q squared times a constant, which can also be precisely determined. Okay, so first observation is that I wanted to make a remark, which is connected to a remark that sometimes in the numerical simulation got wrong conjectures. This was the case for this model, though it is just a one-dimensional model. You see that this scaling or exponential log Q square is quite a sharp a sharp slowdown when Q goes to 0. And in fact, the physicists made many simulation and also analytical works at the beginning, so in the 90s, I would say, and they got it wrong for the constant here that is in the exponential. They got wrong by a factor 2. And this is due to the fact that they neglected some entropy contributions. So I'll tell you in a second what I mean by that. They neglected the fact that in order to do something, it was possible to use a lot of possible paths to get to do something. Okay, so first of all, how one can establish these results. So the upper bound, so we proceed via an upper and a lower bound. So the upper bound is simply obtained by iterating, so properly choosing this K0 where I stop that iteration. And this K0 where I should stop is such that the scale, it was we say in the scale, the finite volume on which I stop, so 2 to the K0, is order 1 over Q, which is the equilibrium distance among empty sites. Okay, you can iterate that inequality and you get this result. But what about a lower bound? Are we just establishing this upper bound, but that corresponds to the real behavior? Why this funny exponential log square behavior? This is can be understood if, in order to understand this, one has to understand the combinatorics behind the East model, so the behavior of the East model. So first of all, consider the East model and start from a configuration which has a single vacancy. Here, depicted on my drawing, I have a single vacancy at site X. If I do an update which do a sequence. I tell you, you can do whatever you want, any sequence of updates you want, but you can create only one 0, besides the one that you had at the beginning. See, I put a square around this one. You leave it, and you create just you do whatever you want, but you can create go through a configuration that have only one additional 0. Then you can go only to this configuration. Because once you have a 0 here, either you create another 0 here, but you have to leave this one in order for this constraint here to be satisfied, or you go back to the original configuration. If instead I give you the freedom of, I give you more money in your pocket, I say that you can spend up to 2 simultaneous zeros, then here is your initial 0 that I give you for free. Then you have 2 coins, 2 zeros in your pocket that you can use. You can reach for sure the same configuration as before, because this one that had just 1 0. Then you can also reach the configuration in which I'm putting a second 0 here. But you can also reach a configuration in which now I am here, and now I'm able to update this site to occupied. So I can also reach a configuration in which I have a 0 in the original 0, then a 1, and then a 0. And I can also reach another configuration in which I have, thanks to the fact that now this site is 1, I had a 0 here, I still have a 0 in my pocket. You had 2 zeros to be able to spend, and you can put a 0 here. Okay, you can continue this game, and it's a nice but not complicated combinatorial argument to prove that if you have in your pocket n additional zeros to spend besides the zeros that I have given you in the beginning here, you will be able to reach only configuration that have their leftmost 0 a distance at most from this x 2 to the n minus 1. So so here, for example, I had 2 0 to spend. I could go up to distance 3 from my initial site. So first of all, it exists a possible configuration which I can reach using at most n simultaneous zeros, which has a 0 at this position, and there exists no possible configuration that I can reach with this n simultaneous 0, which has a 0 to the left of that. Okay, and this is what I meant by saying that the East model has logarithmic energy barriers. It means that if I have a 0 somewhere and I want to create a 0, I start from a configuration which has a 0 somewhere, and I want to do something on my left, and I want to go to a configuration which contains another 0 at a certain distance here. Then, in order, if this distance is L, I will have to go through a configuration which contains log in base 2 of L simultaneous zeros in order to reach that configuration deterministically. Okay. So now that if you have this information, now it's quite natural to understand why the scaling of the relaxation time is really the one that we find with the upper bound. So exponential of log 1 over q squared. Why? Because we are in the model, which is, we are in the process, which is the stationary process evolving starting from the equilibrium measure. In the equilibrium measure, the zeros are at a distance 1 over q. So for sure, say I'm considering the infection time of the origin. So I'm sitting here at the origin. The first 0 on my right will be at a distance 1 over q. So in order to be able for the first time to update the origin, here my origin, I will have to wait to go through a configuration contain log in base 2 of 1 over q empty sites. Hence the fact that the infection times is certainly bigger than the first time at which I see this log 2 of 1 over q empty sites, and so case like that. So then to determine the exact constant, that's why I said before this this sentence with this entropic factor. To determine this constant, to have a nice lower bound which matches the upper bound, one has also to consider which are the possible ways in which I can go to that configuration. One has to take into account the fact that there are several ways in which I can several possible paths which I can use to cross this energy barrier of creating log base 2 1 over q empty sites. Okay, so this is more sophisticated. Determining the constant, finding a lower bound with the right constant is a bit more sophisticated. It requires some combinatorial argument that tells us how many different configuration I have with this number of empty sites that can be reached from just a single empty site at the origin, at a certain site. Okay, and I want also to say that also in dimension bigger than 1, sharp results on this for this East model are known with the exact constant in the scaling. They are due to the organizers in particular, and to Fabio Martinelli, so to Alessandra Paul and Fabio Martinelli. And the scaling is the same, is always exponential log q square coming from this logarithmic energy barrier with a different constant which comes from this different entropic factor in the different dimensions. Okay, so that's for why there is this scaling for the East model. Now, I told you yesterday that 2 stepping stones to understand the behavior of this KCM is to understand the behavior of the of East and of FA1F model. So FA1F model is the other, I would say the most simple model, is the model in which the constraint says that to be updated on a site, I need to have at least an empty nearest neighbor. So what happens in this case, if I give you a single empty site and I tell you, I start with a single empty site and I tell you that you have just one additional empty site in your pocket. How far can you go with this initial empty site? So now you can empty a site on your left. But now, since the constraint is looking to the two nearest neighbors, this site which was originally occupied can be emptied because its constraint is now satisfied thanks to the 0 that I put on its left, so I can fill it. And you see, the net result is that with a single coin you had in your pocket, you were able to move my original empty site of one step to the left. Okay, so here the behavior is very different from the unnoticed model, thanks to the fact that on a site I can benefit of the fact that I was able to induce an empty site on my left. So now, essentially, what is roughly the motion on this when I go to the regime of a small q, essentially the motion is driven by the fact that the single vacancy can move of one step by creating an additional vacancy. So I had a single vacancy here. I was able to create another vacancy here just by to move it on one step just by creating a single vacancy. So, and the rate to create a single vacancy now is so the time I have to wait in order to create a single empty site is order 1 over q. So just have to wait to overcome the barrier of size 1. And so, at least in one dimension, it's not. It doesn't come as a surprise. The result that say if I want to compare with this in one dimension, now again typically empty sites will be of distance 1 over q. So I'm sitting here at the origin. I have to overcome this distance here, which separates me from the first empty site. So I'm here at the origin. So the distance is 1 over q, and I have to reach it with a sort of random walk, which can move to the right and to the left. Here there is complete symmetry, and it moves at rate q. So the typical time to make a move is 1 over q. So I will have a 1 over q in front times a time which is square of the distance. So hence the scaling 1 over q to the cube. Okay, I don't want to enter in the powers of the scaling for the other dimension, but just want to say that in any dimension, modulo log corrections in 2 dimension, it is a power law scaling. And in dimension bigger or equal to 3 is always 1 over q to the 2.
Cristina?
So now, yes.
Can I ask you a question?
Yes.
So here in the what you were explaining is that basically the spectral gap is related to the time that you need to move this sort of mobile cluster of particles that can change the origin, right?
Yeah.
And doesn't it bother you that maybe 2 different mobile clusters can interact between them and create some mess around? So
okay, so for the east and for the F1F model, the clusters are very these regions that move around and that allow relaxation are simply single empty sites. So there is nothing. But already you can see that, for example, for FA1F, these single empty sites, when they meet, they can annihilate. One of them can be annihilated. So they are not, okay, so if the question is, you don't have to be in mind some sort of regions that are conserved and that move around. Because when they interact already here even for FA1F, the easier case, you see that this single empty site that induce relaxation, when they meet, one of them, especially if you are in the regime Q20, one of them may disappear. So they do interact. But the point is that what makes things feasible is that we are considering the stationary process, which is started from the equilibrium measure. And so we will always be working for the upper bounds with the variational characterization of the spectral gap. So with the Dirichlet form, which is a quantity that you can manipulate, in which you can insert, if you have a strategy to make the essentially, okay, I don't know if it's understandable, but if you have a strategy on how to make your units that make you relax move, you can insert it on the Dirichlet form, making sort of path arguments and make it work. I'm not, okay, yeah?
Yes, so let me put it in another way. So here, for example, if you have two of these cluster moving and they collide, one of them may disappear, but you always have at least one. They cannot both disappear.
Yes, they cannot both disappear. So this is related to the fact that there is you can never enter if you have at the beginning you can never modify the backbone of your configurations, the backbone being the sites that you will not be able to update your dynamics because there is no matter what you do, there is no path that allows you to empty them. So here, here it's okay. In principle, if you start from a certain configuration contains some zeros, they can collide and you can kill all of them and you remain just with one. So if you are in, say, you are in infinite volume with occupied boundary condition or whatsoever, but the mess is not. So the mess is controlled by the fact that we are evolving with respect to the stationary process. So we will always be able to reuse the fact that so we are not able to use the fact that around itself this single empty site leave equilibrium. That's an important point that we will see in the last lecture, because though you are able to move your empty site, since your future evolution depends on what you did, depends on how you were updated. Sorry, because see here, here, for example, this site is updated, and what I'm putting here influences later the behavior of this site, because it influences whether its constraint is satisfied or not. So you don't have to think in terms of if you are not at equilibrium, you spread around the equilibrium all the time. But for the stationary process, you can use this variational formula to enforce the fact that you enforce the you use the fact that you know that you are at equilibrium to arrange to allow yourself have these structures that that allow you to relax.
Okay, thanks, Cristina.
Okay, I still have some time. Yes. Okay, so I wanted to move to, so I gave you the explanation of the behavior of these two models, to these two key models, and now I want to move to trying to, as promised, to give you an idea of the different universality classes among these kinetically constrained models, because it wouldn't be so fun if for each model we had to understand its behavior one by one. So there is a way to, so there are different behaviors already in 2 dimensions. We saw that there are cases in which there is a definite critical density transition, cases in which the scaling is exponential or power law or exponential of log 1 over q squared. What I want to show you is that these possibilities that I gave you with the models that I with this table of different possible scalings of the infection time that I gave you yesterday, exhaust all the possibility in 2 dimensions. And not only, if you give me a possible constraint that you invent, it's a matter just of verifying in a finite number of operations certain geometrical properties to decide to which class this model belongs, whether its scaling will be exponential, power law, or exponential log square. Okay, so to do that, I have to introduce some geometric notions, which are quite easy, and the nice part is that they are common to the bootstrap percolation. So if you understand the in order to understand the universality classes for these kinetically constrained models, we have first to understand those for the bootstrap percolation, which are well understood, and then we will be able to understand ours. So, okay, so first of all, I need a geometric notion, the geometric notion of stable and unstable direction. So I'm in 2 dimension here. I will stay in 2 dimension for the rest of today because today is almost finished. So, and I want to introduce the notion of stability of directions. So U is what decides, is what contains the constraint. So you recall that I have the freedom of choosing any possible constraints which are finite range, but they do not have to contain the origin. So I had the general frame of yesterday. So now that you give me the constraint, the first question that I look at is if I fix a direction, U here on the plane, whether if I start from a configuration which is completely filled on the direction, on the half plane, which is perpendicular to this direction in this in the negative direction, so this plane here, and from a configuration which is completely filled here and completely empty after otherwise, whether by running the bootstrap dynamics, so the deterministic dynamics on this configuration, the configuration is stable in the sense that none of the sites can be empty. Everything here in the occupied part belongs to a blocked cluster, or unstable, meaning that some sites can be empty. Okay, so examples immediately to understand this stable and unstable direction. Ist model. Ist model in 2 dimension. Ist model in 2 dimension is the case in which, in order to update a site, I go and look to my neighbor to the right and to my neighbor above, and one of the 2 at least should be empty. Okay, so the West model here. It was a trap. So the case in which I need an empty site either on the left or below. So now consider this configuration, which is half filled and half empty. This configuration is blocked under the dynamics. Why? Because each of the filled sites have the constraint which is not satisfied. Instead, if I consider this other direction here, this direction is unstable, because each of the sites have the constraint which is satisfied here on the diagonal, so I can empty all of them, etc. Instead, if I was so the stability of a direction depends on the choice of the constraint, of course. For example, if I was considering one neighbor model in which I need just one empty site, so the FA1F, both direction would be unstable because it is enough to have one empty site to empty its neighbors. And if I was considering the model which is northeast, the one in which the constraint requires empty sites both above and to the right, then both direction would be stable. Okay, because you see that none of the sites of the occupied sites have the constraint which is satisfied. Okay, so a simple geometric notion, stability of direction. Okay, furthermore, it's not difficult to convince oneself that once we are given the update family, each which contains all the sets UI such that if at least one of them is empty, then the constraint is satisfied. It's only a matter of a finite number of operations where finite is proportional to the number of these update sets to determine which direction are stable and which are unstable, because each update set defines a certain number, a certain sector of the circle of all direction to be stable, to be unstabilized by that direction. For example, if I have this set U1 here in my rule, all these all the direction which are such that are on planes which contain this subset below are unstable direction, because then all the set sides above can have this sees this subset as being empty. Okay, in the half plane, in the configuration in which the half plane is occupied above and empty below. Okay, so it's just a matter of making a finite number of operations once we have the update sets to determine the finite, the stable and unstable direction. And now I'm just have the time to no, not because it's better to leave time for questions.
Yeah.
Exactly.
Yeah, yes. Yes. So I have a question. So why you write R and G? Why this letter in this picture on the right? R plus R and G.
Red. No, it's just sorry, just red and green, because red is I indicate with in red the stable directions, because stable means that I cannot proceed further. If I start from that configuration, half filled and half empty, I cannot proceed further. The direction is stable. And unstable, like green light, you can proceed, are the unstable directions. So what I was writing here was just that for each rule, you can determine, with each rule in the update family, you can determine which direction are unstable thanks to that rule. And then at the end, you can sum, you see, for this example, I've chosen U1, U2, and U3 as update set. For each update set, I determine the rules, the directions which are green are unstable. And then for the whole model, the direction which were green for at least one of the rule are green, so are unstable.
Mm.
Okay, it was just.
Okay, thanks. Is there any question? So if not, so let us thank Cristina for this second lecture. Okay, so thanks. And